I'm getting, let's see, pause for a moment. Let me get just like about a minute. I'm just going to make sure I've got this set up so I can start my talk. And then actually while I talk, I'm thinking, let's see, picking up a little bit of, what do we see? We're seeing something over here. We're seeing the cable, let's see. This will take some time. Actually, what I'll do is I think first I'll jump around a little bit. First I'll talk just for a minute on the ARM, and then I'll go into the processing environment that is the Java environment that was used to do all the image processing and then talk to a Arduino. So I guess I'll start with that. This is an ARM that Will Kinley and I, at least Will built the hardware. So Will built the robot arm, I want to say around 2008. So it's what, about whatever number of years ago that is, 9? How time goes by. Anyway, originally this was controlled with a different controller and also a different Windows application. But it was a more involved, complicated environment with a steeper learning curve, I would say, anyway. So now the challenge is sort of the ARM is being reprised. And what we have here is we have a fairly simple system. We've got a web camera, and you can see there's a live image. In fact, slightly enhanced with it actually recognizing some features in the image. But more or less, that's the live video image appearing on the left. And then also we have a simple ARM, which Will crafted, and it's composed of 2 hobby servos. But it makes for a very elegant and easy to realize design, I'd say. And the purpose of this is to allow some investigation into a simple robot arm that utilizes rotational joints. So in other words, we have an arm that has a shoulder that can rotate and then an elbow that can rotate. And so with those 2 joint angles defines positions where the hand is located. And the kind of one of the challenges here is to understand where the arm is in space, and also to understand where a target object is in space. Like if we can place a puck, and I ask it to, let's see, I can ask it to show the puck there. So now the processing application is taking a video image and analyzing the pixel data, in this case, really looking for a dark spot, and a dark spot of a given size. And in this case, you can see we've identified it, and we're reporting that location in screen pixels. So the far upper left is the origin. I can't quite get it there. You can see very small numbers. Oops, what is that? The black thing is the mouse position too, by the way. Anyway, so there is the recognition of that object in Cartesian or 2-dimensional space, where so the first number indicates the x-coordinate, so as the puck moves to the right, you can see those numbers increase, and the image size is roughly 600 or 640, and then as the puck moves down, the y value increases.
I'm sorry, I didn't hear. What's the number of the column?
Oh, that happens to be where my mouse is right now, and that's for diagnostic purposes. Then also, I'll switch back to where we're recognizing the smaller dots on the arm, and not so much the puck, although it will recognize that too. Oops, and we'll try to cover up the table. I do have a mask, but the mask actually obscures a little too much of the area, so I'm going to try to work without that mask turned on. So let's see, from here, we have the ability to control the arm manually. So here's the shoulder being moved, and then here's the elbow. And it's pretty nimble. It's fairly quick. It's not a very powerful arm, but nevertheless, it's a great opportunity to explore what you can do with a two-dimensional arm and not using any complicated or expensive hardware. So, okay, with this said, the thing I want to do while I'm kind of introducing processing is I'm going to start the process of a calibration sweep where what's going to happen, and as you'll see, hang on, let's see, I'll just start it and make it pretty apparent what's going on. Oh, here I'm showing a virtual puck in the hand, and the recognition is a little difficult because it's having difficulty recognizing two hand points. What I'm doing is I'm recognizing this point and then calculating the midpoint. But because our outer hand point is being a little flaky, let me see if I can tune that. Let's see. See if I can get that reading a little better. Yeah, okay, we'll see how we do. Now, it may not have a perfect demonstration. It even thinks it's down here, but that'll change. Okay, what I want to do is I want to do a calibration scan. And I want to make sure, let's see. Okay, what we're seeing now is a calibration scan. And what I'm doing is I'm saving the position of this virtual puck or the hand center as I do the scan. So what I'm doing in my processing program is I'm feeding a serpentine pattern where I'm sweeping the elbow joint through a range of numbers. It turns out that the numbers that I use is 0 to 1,000 for the servo position. So while I sweep the elbow through 0 to 1,000, then I increment the shoulder joint location, as you see it jump, and then increment the elbow through its range. Now I'm stepping the elbow in a fairly fine fashion, but in order to get the calibration scan to complete in a reasonable amount of time, I'm stepping the shoulder in a fairly coarse fashion. Now the result of that is what's going to happen when let me explain the purpose of this. The purpose of I'm saving all these points, and without having to do any complicated mathematics, with an arbitrary camera position that might be skewed or off a little bit, as long as the camera remains attached firmly and not moved, what's happening is for every shoulder and elbow position of the arm, we're acquiring an XY screen coordinate, like I showed you earlier as we move the puck around. So what I'll be able to do is I'll be able to interrogate what amounts to a great big... Oh, sorry.
Recording pulse width, don't you?
Yes, yes. So when I say shoulder and elbow position, I mean the pulse widths that are being fed to the servo. So those numbers that I said 0 to 1,000 that roughly correspond for those in the RC servo world between 1 and 2 millisecond pulse widths is scaled from my 0 to 1,000. So anyway, this will continue to run. And actually, it's not doing too bad. Let's see if I can kill a little more time. I hate to interrupt the thing. Any questions so far?
So what you're saying is rather than doing the math, you built yourself a matrix that says, okay, if I want to get to here, here's the values to use.
Yes, yes. And in fact, it's not even a matrix, but it's just a long table that has the XY screen position as calculated and the elbow and the shoulder positions as being swept through. And I sequentially, save all those points. So there's, in this case, I'm going to say 10,000 points. Yeah, this isn't going on with a little Mega 32. So maybe I have 10,000 points in a table. So to iterate through that table, what I can do is I can ask a question is, where is the closest recorded location that we found with this process for a given, if I set the puck on the table, if I set the puck on the table, then I can find the shoulder and elbow position that's closest. But Will will explain after I get through running my mouth, he'll explain maybe a method of fine tuning that. Because the problem we can see right now is if I happen to place the puck, I don't know if I can reach, I can stick my finger in the, I don't want to goof up the camera. But if we happen to place the puck in an identical to one of those locations, then the elbow and shoulder location will be perfect. It'll just align perfectly. But if you can imagine if I drop the puck somewhere in between, like between the two rows, Now we've got a little bit of a problem is there is no exact location. So that I will never find exactly a sweep position of the hand that matches up to my puck, so that I have a problem. But Will has a solution to that involving just a little trivial math. But now, another way to approach this might be, if you had a little more time, is just maybe do twice as many shoulder, or cut your shoulder increment by half. And I think that would get you to where this hand would accurately acquire a puck. But anyway, so let's see. Well, this
hey, Ron, a quick question. Why the virtual puck? I'm not sure I understand.
Oh, well, the reason for the virtual puck is I don't have the center of the hand identified with a target. So I have a target on the wrist and on the finger of the hand. And so I'm just doing a quick calculation to find out where the center of the hand is.
Okay.
Because that's really what I'm interested in. In other
So-
words, for the purpose of acquiring a puck, we want to know how to get the puck into the center of the hand, if that makes sense.
Okay, but the puck is, the virtual puck is just the visualization
Right.
that you're,
Right now, that's
you
just
could
the-
do it with the actual virtual puck.
Right.
Because
right.
all you're calculating one point, basically.
Right. But you can see, while we're talking virtual puck, because of the, I can fade those out a little bit. I do have a transparency control there, so I can make this a little dimmer. But you can see we've got some virtual pucks that don't really belong. When it lost the fingertip, look, we've got some garbage over here, but it turns out that if I search this list, I won't find those because I won't place a puck there. We consider the active area of the hand a rectangle is more or less where most of that information is being recorded. So we're not saying that the hand, we're not recording every last point that the hand can reach. And I did stop the hand. I have a table to keep it from running into the camera pillar. Because by design of the hand or the arm, it will kind of collide with that pillar. So I did keep the scanning process away from that a little bit, and also kept it from running off the table. Because when we get to this position, the arm isn't nearly as straight or unflexed as it was in the original scans. So there, I'm going to stop. It just slightly ran off the table.
Well, it stayed on the table, but it ran out of your window.
Oh, out of the window. There you go.
Your coordinates, does that signify some other encoding, like it's 1,500?
Oh, I'm sorry. You're seeing a digit 1 for the blob number, and then there's a space, could be a little larger.
Oh,
And that's the XY, yeah. And then in the gray, you're seeing the distance between the wrist and the fingertip is 63 pixels, it looks like roughly. And then you're seeing that calculated virtual center of the hand point in the gray.
So do you do interpolation of coarser movements? Like whatever it is. It's like you find a median value between 2 points if it doesn't fit with either or something, or if it's between. Do you actually do that or?
Oh, now with respect to what?
We'll talk about that.
Yeah, he'll talk about, with respect, yes, yeah, as far as to locate a puck that's not identical to one of these locations and generate, yeah. That. And then, of course, over here we can see the shoulder and the elbow positions as they change. You could have made it a little faster. My fear was, though, that this laptop might be laggy a little bit compared to a desktop computer, because one of the things that is happening here is as we sweep, there is a little lag with the camera. So in other words, when it captures the image of the puck, it may not be exactly where the hand is or was. So there may be some mismatch there.
And your XY is pixels?
Yes.
Every
Yeah.
pixel is a point.
Yeah, every pixel is a point, yeah. So again, this full screen or this window is 640 by 40. Anyway, that's okay. Oh, you're just about there. In fact, I know we're just about there because our shoulder is at 900. I think this is going to be about the final sweep. So rather than interrupt this presentation, I'll be able to complete this demo and then I'll move on to I think this is kind of the exciting part of the thing, but I'll move on to kind of the introduction to what processing is, what this environment is, and also a at least the approach I took to learning a little bit about the environment, and I am not by any means a Java expert. I have written a few applications, dabbled with Android, but maybe in a way that's helpful to know that I'm not a wizard when it comes to that language. But I find the examples that are presented and the tutorials are really good. And this processing environment has been around for like about 15 years. So it's well supported, and I'll have my information on that. Okay, so let's see. Where are we? Oh, we're at
Ron,
1,000.
one last question.
Yes.
The application that's running there, is that a processing application
Yes.
that you have put together?
Yes.
Okay.
Yes, so I'll have all the code available for that, if somebody
Okay.
wants to look at that.
We'll put it out on the GitHub.
Yeah.
Okay.
Okay, it's kind of crude, and again, it's not a great representation of how to write Java. And this will evolve a little bit. I think I'll incorporate some of Will's refinements and maybe clean it up a little bit, but I can put it out as is. Okay, we should be about done. Let's see, shoulders 1,000. I think I'll look at the console here. It should have saved. Yes, hand position saved. Okay. So there they are. So now what we can do is we can, with that table, if I click on a given location, simulating a puck, I didn't quite get we drop the puck on the table and go to the puck to be done. So what I'm going to do is I'm going to simulate what would happen if we, with this puck, let's see, I'll get rid of it, I'll make this a little more faded out. So ideally, right now, it would take a few lines of code, but I won't demonstrate how bad I perform in a room with more than one person. So anyway, so rather than that, what I'll do is I'll just go click. In fact, we'll leave the puck there, and I'm just going to click on it, and because my mouse is basically, you can see the black coordinates if they're movable. Get some light stuff there. There we go, 206. So it's roughly 299, 190 roughly. So I'll click on that, and let's see if it moves over. It might be violent, but it'll go fast. And I want to stop short in the future, but for now we're going to go for it. Bang, so there it went. And I think because it bumped it, it probably, in fact, let's see if I can nudge into it. Maybe. Well, okay, maybe it isn't that refined. Let's see.
Put this in.
Let me put my puck on a scan. Let's try that. So there, that's it. That's sort of an ideal puck, hopefully. Let's see how that works. Okay, let's see. Oops, I think it went for it, but it knocked it out of the way. So
The hand's in the right place. The puck-
let me fade out the alpha. Yeah, sorry. So anyway, I'll click. Let's see. Yeah, the letters are seem a little bit fussy. Here we go. But anyway, you get at least an opportunity to see that something more or less works and not perfectly refined yet. But anyway, so the question is, what is behind this application and how did we get here to create this? So that's going to be phase 2 of the talk. So let me move on, or let's put this aside for a little bit. In fact, we've saved our data, so I can bring this back later. And I will bring up my rather crude and simple introduction, very crude, hardly worth showing, but I will demonstrate that I at least produced some slides for a presentation program. So this will give you the background. Okay, let's see, slideshow, I think that's it. And do forgive me, okay, so this is the history. Two grad students from MIT, Ben Fry and Casey Reeves, if I'm saying his name correctly, developed processing. And for those of you who are familiar with Arduino and the Arduino environment, how many people with a show of hands have seen Arduino environment or played with it? Okay, so a fair number. Okay, that environment evolved out of processing. So processing was there first, although processing is Java-based, and the Arduino environment is C++ based. But really, as far as the interface and a lot of the ideas, they're common. And that's very good because helps reduce the amount of stuff you have to learn. I think there's a limit to how much we can handle. And also the fact that that environment supports at least reasonably complicated projects. Some people build very complex software there. But then in some cases, if you're really dedicated as a software developer, you'll want more advanced tools, and you're dealing with larger and larger projects with many people, then maybe some of those environments don't hold up as well. But boy, for getting started in a one-person thing, not a bad way to go. So let's see. Yeah, so there I mentioned that the Arduino sketch whole thing evolved out of this system. And there's lots of documentation. And I was going to talk a little bit about Java just for people. Do we have anybody here that's not messed with Java, but they're C++ or C programmers? Okay, a few. Okay. Well, I just really, what I wanted to say just as a brief introduction, and I'm not going to try to compete with the enormity of all the available documentation and things that are available out there. But just from the standpoint of, hey, I know a little bit about C, or I've worked with some of the Arduino stuff, and I've done a little code there, what's going to be involved with Java? And what I would say is all the low-level syntax, all the low-level constructs, the looping, if-then, all those ideas, most of the variable declarations are very similar in Java. Only a few things that are little gotchas, I think, and can be gotchas, is, for example, it supports signed types. At least at the lowest level, it understands numbers as being signed. So a byte that normally you would think of possibly unsigned would be 0 to 255. Well, Java will see that as plus 127 down to whatever, minus 128, that range. So you have a few things to deal with, and if you get into anything that is involving caring about values that you would store in a byte or in a 16-bit number or anything like that, there's information out there on, hey, how to deal with this. If you're not just an inherent wizard with binary arithmetic, then there's stuff out there to help you deal with that. The other thing I'll mention is just because I think in just basic program, I think about variables, integers, and floating point, scalar, single values, and also then pretty quickly though, like for example, dealing with this ARM. I have a couple of cases where I need some tables, and those are typically one-dimensional tables. And so there's a little difference in the syntax and how you will allocate an array, for example, and I'll just give you an example there. I have a thing called byte table. It looks a little different than you can see in C. And again, many examples. And the other thing I'll mention just quickly is when you get into two-dimensional tables, Java really, the native beast understands one-dimensional tables, and it creates two-dimensional tables by actually creating lists of one-dimensional tables anyway. But nevertheless, there's some neat things to manipulate two-dimensional tables. And as you might expect, a little search, I wouldn't even bother with the URLs here, is that I searched for 2D arrays, Java, and immediately came up with some really nice documentation on some of those things. Let's see, so I think what we're going to do is, and I'll say one more thing about Java. For me, I felt it handy to just veg out and watch some tutorials. In fact, there was a Stanford University had created an entry-level programming class featuring Java, and I kind of vegged and watched a lot of those tutorials, and those helped me. Ultimately, though, programming is all about experimentation and playing around, and then combining that with theory and that sort of thing. But the web is such a great resource to be able to ask questions and find out information. So I guess what we'll do, this may take me a second. Let's make sure I'm logged. Well, we'll see if I'm logged into the web here. Oops. Let's see if I can bring up my browser. Lost it. Wait a minute. Oh, maybe I've got it on my desktop. Could we pause the video for a second?
No worries.
Okay.
Yeah, don't worry about
All
it.
the post editing.
Oh, gosh, okay. Let's see how long Ron takes to find his bloody browser. I'll be sure to use lots of profanity so I know this gets cut out.
That's right.
But then again, sometimes we're pretty sloppy too.
Let's see. Does anybody see I think I copied a bunch of stuff off. Wait a minute. I don't even see Firefox. Wait a minute. I think I have Firefox on here.
I would encourage on this also, just because of that
That buzzing noise?
buzzing noise out there. We might need to get the audio cleaned up.
Okay. Let's see.
No, it's just a mic. Just as nice. How's it go? Well, no, it's the handheld. Oh, so it's not. No, I'll synchronize it. Figure out. So I guess.
There we go.
Wait a minute. Whoa.
Holy
Whoa. Who's this guy? Oh, sorry. He's here for the beer,
I
right?
know the beer meeting's in the other room.
Yours over there.
How are you?
Or you can sit back here. I'm sorry.
Okay. Okay, let's see. Processing. So I gave you a little bit about the background. It's Java-based. And what I would really recommend is I didn't even want to compete, really, with the elegance of all the documentation that's available for this environment. And anyway, starting with your software download, and this will run under Linux, but I haven't tried. You can volunteer amounts. I should probably volunteer an amount right now. But anyway, it will run under Linux and also Mac OS. And another thing I'll mention that I've played with just only in a little bit is the ability for it to build for a target like Android. But there are some kind of catches there as far as what's supported and what's not. And I have yet to, I can do some basic graphic stuff and some basic graphical user interface stuff, but I'd say I would not be an expert or anything. I can show you later something that runs on my phone. But anyway, and as far as Linux goes, I would think that the support is very good, and I would think if I understand some of the stuff in processing relies on, I think is it Advanced Window Toolkit, AWT? I may have that wrong, but it's basically a lot of software that would be encompassed within Windows operating system. And I believe under Linux, they'd probably have a interface that would work with Linux. And so you'd have all that functionality. But anyway, so once you download the program, and it's whatever it is, 100 or a couple hundred megabytes, then from there, I want to just go back to the main screen. So with the environment downloaded, one thing I can recommend is the examples are fabulous. And one thing I did find with examples is when you download the environment, you have the examples, which I'll demonstrate, are readily available. But I kind of think that the examples that are also online that are written in JavaScript are easier to access in some ways. So you can quickly browse. For example, let's see if we can pick just some simple, here's one on recursion, okay, shows you how to build a recursive function and with the drawing circles. So it's only about 10 lines of code, as recursive things often are very short, but take a little bit of mind to get around what they're doing. Anyway, I have the ability then to quickly look at these examples to find things that I'm really interested in doing. If I'm just interested in doing very fundamental things, here's one, just how to draw lines, and it shows you the functions. that would be used to draw lines and points on the screen. Well, that's not terribly exciting, but then there are just a number of examples, and so that's I think a big thing anyway. Also, there's a reference readily available. With the advent of having lots of examples, often you have a lot of elemental functions that are really helpful to see some explanation on those. So their reference, which is online, but also I believe some of this is also offline, so that when you download the environment, you don't necessarily have to have a hot internet connection to have access to at least some of this information. But for example, we can explore anything like, okay, we want to draw an ellipse, it shows us the parameters for the ellipse. And also this reference is executable from the environment itself. If we have the ellipse function, we can right-click on it and ask to see the the reference manual for the this particular element. So I found that to be very helpful. Also to mention that processing has the Java environment, but closely linked to that, because processing was really founded by people interested in visual arts and really for an artistic kind of bend on the whole programming environment thing. These folks were very much into the graphics aspect. And it's also interesting to note that in a number of experiments with introduction to programming, they found that folks that had access to an environment such as this, where they were able to do some of the visual things with programming, they were much more apt to keep their interest in computers. And I have to say that's what got me interested in computers from the get-go, back to Apple II days, is the ability to create pictures on the screen. That was for me, that was my interest initially. So anyway, but things have progressed along. And another thing to mention about the Java environment is traditionally Java, I think, might be thought of as being slow. But I think as time has passed, it has evolved. And one of the things, it is an interpretive language, but it partially also relies on compiling code such that you get a lot of the advantages of compiled code. If you enter a loop that executes 1,000 times, the Java compiler is going to create native machine code for that code typically. So you do get very close to the same performance you'd see in either native assembly code writing or in a language like C, for example. And another thing to mention is when you get into involved graphics, 3D graphics and whatnot, then a lot of that functionality is also incorporated within libraries that run in very optimal situations. In other words, when you're rendering a three-dimensional model, most of that is being done by graphics hardware in a very tight grouping of code that is running on the main processor. So again, those things that we might consider negatives are not so much.
How big an environment is that? How big is it?
Oh, how big
As in megabytes of?
Like 70 megabytes.
Okay, Steve got a good answer. I haven't even thought about like how much memory it occupies when it's running.
Well, not so much how much it's running, it's what's on disk. You download like.
Yeah, 100 megabytes or
Yeah.
Okay.
yeah, and there's probably more than 100 libraries. Oh, and let's step into the environment. Enough of me running my mouth here about some of these different things, but let's see. Let's get into the physical processing environment as you see it when you load it. Oh, there we go. Okay. For some reason, I always get this message even when I uncheck this. I haven't figured that out. So it starts us off with an empty sketch, but yeah, or a program. Anyway, so we were ready to go. Anyway, but what we've got very quickly is, okay, let's see some examples. Let's start with an example rather than just an empty sketch. And this is where we have a lot of different goodies. But I'd like to look at one. Let's look at video capture, for example. I think because that's sort of an interesting thing to do. And it's something that often, in the old days, that was something you had to fight a little bit to get something to capture video from the camera. But here we'll have an example, and this particular one, here's the code, which I'm sort of whisking through. And this particular example, what we're going to do is we're going to capture an image, and then what we're going to do is save that image in a table. And then what we're going to do is take images that are being captured in real time and subtract the fixed background image from our current image. Let me just run it so you can see what happens. Let's see. Okay. Here's a picture of me. Okay. And now what I'll do, this may be a little bit weird, but let's see. Well, we'll have the effect of the background. That'll be weird. Okay. So let's see. When I believe, let's see if I click in this window. There we go. So there what happened is, I'll capture another. If I don't move at all, the idea is that the pixels are black. So if I could stay perfectly still, you can see I look like just a highlighted, very dark complected person, I guess. Anyway, but there you can see, and the idea here is that if we have a static background, could be very handy. Let me try to get something that not looking at the background screen, which is kind of. But what it would allow is this kind of idea, although more like if you acquire background images more frequently, we can see where motion is happening in a frame. And in the context of robotics, that can be very useful in detecting a moving robot. Let's say you have an opponent. Well, if we acquire a background image, and then that robot in the background moves, we could do kind of the blob detection like I was doing on the robot here, and we can actually get a range of pixels where we detect motion. So that could be quite handy. Now, you get into a little bit of a difficulty when the camera is in motion. So now you have a more complicated problem. But for a static camera, the background subtraction can work very well. But once the camera is moving, you've got a new problem and a more complicated problem. So let's just real quickly, so here we've got this program, and this is an example. What's involved is really nothing more than taking the difference between the two image tables, which it turns out in processing, an image is represented as a one-dimensional table. And it's a rather long table, so that if we have a 100 by 100 image, let's say, there'll be 100 elements along the top row of pixels, followed the next 100 elements is the next row, the next 100 is the next row. So if we want to access that really as a two-dimensional object, we end up doing a little bit of mathematics, which is really multiplying one coordinate by the width of the image, which is 100, and then adding the other to get a particular XY position in that. But an example like this is you can tear it apart and figure out what's going on in a reasonable amount of time. Now, something else used in this example, if you were a newcomer, it looks, okay, what is all this weird stuff with these little arrows? That gets into the realm of go look at the description of how pixels are stored and also how you access information within or color information that's embedded in this case in a 32-bit integer. We embed red, green, blue, and also really transparency. But for the purpose of this, we're embedding 3 numbers in a large number. But this example I consider as sort of intermediate. But if that was your interest, is hey, I want to be able to do stuff with computer images, this might be a place to start. And something else I will mention is that processing supports OpenCV. And I don't know to what extent, but OpenCV is a collection of libraries that are oriented toward doing image processing. And in that case, you'd open up a sketch and you would acquire an image and feed it over to OpenCV for processing. So there is quite a large area that I elected not to investigate with this application. I implemented the blob detection and all that stuff natively in Java, but that's another route to take and another area to explore.
Okay, so there's, if I go in to look into the examples, I won't find a blob detection example. But did you step out of processing to create your blob detection?
No, it's written in processing.
So it's written, so you just created a blob detection algorithm
Right.
in processing without leaving the environment.
Right.
Okay.
And
All right.
I'll kind of give, I'll give kind of a brief step through, but I won't spend much time on that.
No, I understand. I just,
It's just for the general
Yeah.
feel.
Do you have an idea what the frame rates are?
Well, pretty close, in this case, pretty close to 30 frames a second. I guess it would have been nice to, you know, to actually, let's see, with this sketch, hang on. Let's see, find it. So in this sketch, let's try something. And if I don't catch it the first go, we'll give up, because I won't suck up time. But I think what I can do, I think there's a variable called frame rate. So I think I'll tell you what, I'll print it in the console. That'll be the safest thing, rather than print it on the screen. So, whoops, and forgive me, I don't use this laptop to do any programming. Okay, so println, I'll just println frame rate, let's see. I think that's the name of it. Yeah. So let's try to run this sketch. And I don't know what the freaky number, oh, sorry, there's another number being reported, but you are seeing between the rather large number, which, but that number is the number of pixels that have changed. But see that other number that's 60?
Yeah.
So it's acquiring 60 frames a second from the onboard camera on this laptop. So it did look pretty fluid, didn't it?
and knowing Ron, this laptop's really crusty too.
What's that?
And knowing Ron, this laptop is really crusty too.
This laptop is an intermediate range. It's I don't know, $500. I didn't go in for the fancy one, and I really wanted, like a couple of grand. I thought, I typically destroy these. This one I let slide out of the car last meeting, and the one before that I physically ran over with my car. I wanted to protect it. I was going to get my car inspected. Didn't want it to get stolen. Laid it up against the garage. And it flopped over and got under my wheel. I'm backing out, and I just felt this uncomfortable. And I didn't open the bag until I got home from my inspection. Car passed, but the laptop didn't. So I ended up in that case, I ended up with a cracked screen, and it was really kind of cool because I used that cracked screen that was still functional with all its little bizarre crunches. I used that as a screensaver for about the next year. So whenever my laptop would go into screensaver mode, it would display that picture. And it's amazing how disturbing that image was. So finally I rid myself of that image. But it was really
A reminder.
yeah, a reminder. Boy, but I was lucky. Really, I stopped the car that quick. So I guess it does say something about I'm not too repulsive in my driving. Anyway. So let's see, let me just see if I can dig up another, I'll pick out some of my stuff I've been playing with. But as you can see, we got a million different examples, and actually before I go into a couple of my demos, let me go in and show you how you import libraries, because these are the things that, it's just so easy in this environment. So if I go to this thing under Sketch Import Library, what it will do, and then I say Add Library, it'll bring up a list of libraries that have been contributed and are, I guess, part of processing as far as without going out on the internet and searching. There are certainly people with unregistered libraries or whatever you call it. You can get their stuff and they'll tell you where to copy the files. But here we have a list, and you can see some things. I did install someone else's blob detector, but I haven't looked at that yet. So someone wrote a blob detector. I played with Bluetooth a little bit. And I'll show you a little example of building a graphical user interface just real fast. But you can see just a myriad of different goodies, and you name it. So you can spend a lot of time browsing YouTube videos, and you'll see what people have done with different libraries and so forth. Also, here we have the modes that this thing can be generate code. For example, Android mode. You can download that and then build projects for Android. But again, there's a little bit you have to know. There are some libraries tailored to building stuff for Android. Another one is P5JS. Let's see, so that's JavaScript, and that's if you want to embed code into a web page. Like some of those examples I showed you were actually written in that and then compiled for the, or executed by a web browser. Also, if you're a Python person, there is a Python mode. Haven't played with it. And I don't know what REPL is. Anyway, that's a lesser, I'm not sure what that is. Let's see, oh, then tools. For example, one is the, let's see, the GUI Builder. I think I have that on here, I hope. I'll tell you what, I'll just try to install it anyway. So here's an example. This is a builder, a tool that helps you construct graphical user interfaces without having to numerically figure out where things are. And that's how the ARM application was built using a simple graphical user interface gizmos that don't have a visual tool to build or to situate them on the screen. So the interesting thing, though, or one of the things about this G4P is it does require a Windows environment, so it's not going to run on Android. Okay, let me try to load. Let's see. Let's go right to the tool. Let's see.
So it'll only run on Windows and won't run on anything else?
Yeah, with this particular builder. So let me just show you real quick. Here is, whoops. Oh, I think I might have freaked it out.
Resize it to 0 or something.
Yeah, I did something with sizing. Did you see I did a little move there, and I might have found something that's not, let me just restart it.
I was going to say, try clicking on the element in the control bar on the right. It says slider 21.
There you go. Thanks, Steve. Okay, wait a minute, try it again. Still weird. Let me try
Delete it, delete it.
Yeah. When all else fails, delete it. Hang on. You can see I've used this, I promise. Let's try again. It seems to be bringing up what I've already been working on. Let me exit, just in the name of saving some time, let me exit. Restart. If it's something I've been working on for 2 hours, I'd be a little more inclined to spend some time. But yes, I did a little fancy move there, which don't ask me. Okay, let's try this again. So let's go to this builder, and I love this little 2D control, and let's try to drag it. There we go. So that's a 2D joystick. And you've got all sorts of things, sliders, knobs, buttons, the whole works. I might have done it to that one. Okay, let's see if we can exit this and have it. Okay, so now I exit that tool, and it embeds in a sketch the controls that I just created. Let's see if they show up okay.
So as you drag and drop those on there, it's generating the code for the controls.
Okay, negative 70, that's fine.
Yeah, okay, let's get rid of that. Let's see if we can do that.
There you go.
That was fast. Yeah, some people in here think much faster than I do. So anyway, okay. So barring some of the little quirky things here, what we've got is these controls that I dropped, and also they've added some things. In this case, you're seeing in the bottom window there, changes in the control position, for example. Now really what we want is we want the values returned from this, and not that difficult. You bring up the list of methods that are supported by, for example, this control, and it will show you how to access. In this case, this control generates an X value and a Y value, and I think its default is probably 0 to 1. So up here I'd be getting 0, 0, and then I'd have 1, 1 down here. So really, for example, if I wanted this to drive the servos of this arm, a few lines of code, and I could take a value here, and it wouldn't map to the XY coordinates, but it would drive this elbow and shoulder directly. So there's an example of being able to have graphical user interface tools, and these can be embedded right in your main window, or you can create separate windows. And again, there are examples and all sorts of goodies to show you how to do this stuff, tutorials. And in fact, right in our examples here, just as an example, we could look at G4P, which is what we're playing with, and here they'll have all sorts of things. So whatever your interest is, you want a text box, you want whatever it is. Let's see what its showcase is. Let's see if this will work. So here we've got a text box. We've got some kind of a control. Let's see. Let's start. I don't know. Anyway, a number of different little menus and dialogues that were created with this G4P that then report values into the program. So definitely a fun place to spend some time. I'll show you one other example or so, and then I'll kind of just briefly show you this, and then that will be the end of me. So if there's any questions, that would be, let's see.
It does the very Arduino-ish.
Very good.
Very, very similar.
So here's a bunch of stuff. Let's see. Oh, here I did, just as an example, let's see. Spinning head. I was curious, what would it take, how much code just to take a JPEG image and rotate it and throw it on the screen. So here, let's see how much code it is. Not much. Wait a minute. We set up our screen. I load an image, Ron face, and let's see. I can't even tell you what. I must have been just experimenting with something there. I'm not sure. Okay, let's see. A draw head. We got X offset, Y offset, and an angle of rotation. So we have some primitives here to translate the image, rotate it, and a little bit of weirdness to rotate it about a given point. So let's see how that works.
Where you've got a loop, right?
Yeah, and then, oh, by the way, so there's, like in Arduino, you have a setup function, and then instead of a loop function, and I'm not erasing the screen for fun here. So here we have that bitmap being, you can scale it, you can rotate it, translate it. It might be kind of neat if you had a big photograph of an overhead view of a robot contest course or something like that. You could then rotate it, scale it, and move it on the screen, or move a simulated robot about that image. But anyway, so there is just a real simple example of, about 10 lines of code. So let's see, let's say if we scale it by, here, I'll scale it, we'll triple the scale, let's see. Oh, actually.
Got a variable, just change the variable?
Yeah, and the other thing is, let's see, one other thing I didn't mention is, when we run this sketch, okay, we'll run it large. We'll run it, but what I'm going to do is to show you one of the features. If I have this scale here times 3.0, now let me run it a little differently. There's a feature called tweak. Oh, I need to save the sketch. So if you save it first, and then instead of running it, I say tweak. Now what happens, let's see if I can, except I need another, what I need to do is tell it not to be so big. I'll shrink the size of the image that we're working with, so I can, since I don't have a multiple monitor situation here. Nice to have multiple monitors, or bigger situation. Okay, so here we go. And so now, oops, I ran it, I want to tweak it. So I'm going to save it again. Okay, I want you to save it. Tweak. Now, there it runs, and now variables that are constants, like the scale factor right here, I can in real time adjust that. Which is really kind of fun. And so if I'd added other, I don't have too many other exciting, that's weird, I don't know what this is gonna do. Oh, no, anyway, I can't even tell you right now without looking at it for probably 30 minutes. But anyway, I've got another value here that I'm tweaking in real time. So, just awesome. If you want to create something with, you're just trying out a little idea, and you just leave some constants in the program. You don't have to go and write some special graphical user interface controls to adjust those values. You can go in and fiddle directly. So tweak is great. And also in addition to that, which I won't go into, is there is debugging capabilities. So you can put the beast into debugging mode, and you can single step and do all those things if you're familiar to debugging. So just really awesome. I mean, you could just go on forever, but I think it's more efficient to probably see. I'll show you one other example before I'm thrown off the stage here. Oh, and I did say I was going to just briefly touch over this. Okay, let's see. So here I was curious how well would it display like three-dimensional stuff. So let's see if I was doing some concept for a Crow museum. So I was just curious, could I animate a human brain? So I went and I found a model of a brain. Now this computer isn't that fast. Whoops, in fact. Oh, here I was trying to put the brain in a head. And let's stop this one. And I have it set up. One kind of tricky thing is the size of the image is hard-coded. And you can do full screen, which will then size it appropriately, but otherwise you end up kind of hard-coding stuff here. So I'll drop that down to 1,000 by 900 to fit my screen here. Oh, and to complete the thought, as mentioned, I'm not sure if I've completed it, which is, well, the brain isn't registered with the head, and it's lagging a little on this laptop. On a desktop, this screens at 60 frames a second. But I am trying to do a number of things, with this weird text and whatnot. But anyway, 3D graphics are well within the realm of processing. So it's definitely a lot of goodies are available there, and stuff to help you load existing 3D models and all that sort of thing. That's cool. The other thing that's available is two-dimensional physics. But as of right now, I didn't see a lot on three-dimensional physics. So if you want to do physics with cubes and things like that, that might take a little more looking. But I think there is some support. I think maybe Physics Monkey or something like that, if I'm naming that correctly. There's some physics capabilities that are there.
So with respect to like motion of the cube, or
Yeah, no.
motion under gravity?
Yeah, of course you can, stuff like that, if you want collisions and things like that, and linked objects, that's where you need a physics engine now. Of course, to do, for example, let's see. I've got this where I have, so here's some just simple motion where I have particles and I have some physics applied to those. And here, this is a little later, more. Oh, this is running 60 frames a second, so that's good. So the program running in the inset here is just simply objects that are being translated in X, Y with a gravitational force acting on them. You see they accelerate downward. And the interesting thing too is that effect, that fading effect, is really using some of the graphics capabilities wherein we're doing a kind of a blending effect. We're taking the old image and taking about 90% of it and blending it with the new image. And that's in the domain of what you call alpha channel or a transparency channel. So it's kind of cool stuff, it makes for a neat effect. Anyway, that will conclude my demonstration of examples other than I'll just briefly kind of just show you some of what goes behind the robot right here, or what's involved. Any questions while that loads up? Yes.
What controls the rate? Is there like a loop, like
Yes.
Arduino has? and
Good you mentioned,
What
Paul.
controls that loop?
Yes.
That rate?
I might have interrupted that thought. You have a setup, and then in Arduino world, I think you have a loop that runs probably as fast as it can.
Yeah.
Well, here, the loop is a draw function, and that is called typically 30 or 60 frames a second, depending, or unless you're lagging, then I guess it would slow down. But that's the typical scenario. You can tell it, don't execute that draw function more than once if you just wanted to draw a graph and then wanted to keep executing. But overall, that's kind of the idea. And at least so far, I haven't tried to get into any multi-threaded, any exotic processing. I more or less just do processing within the draw function that can be completed in a reasonable amount of time. And thus, if I have an animation process going on, like this robot arm, which I guess you didn't see, I'll fire that up in a second when I'm showing the program. Then, in that case, I'm losing my thought.
So one draw function at the end, and it like basically waits for a 60th of a second, then before it
Yes.
rolls
Yes.
back out and
Yes.
the loop loops again.
Yes, as far as I know, I think that's correct. It might be limited by the graphics hardware, but so far what I've experienced was most of my hardware would run 60 frames a second unless it was fogging like the laptop was. And then in one case, I had it seemed to be limited at 30, although a recent release of processing seemed to boost that. I had a little portable, one of those little Intel Nooks, I think they're called, little i5 little cube. And that seemed to be, I thought it was running slow for the purpose of saving, not dissipating too much power, but I think it was just a software thing.
And then the second question, when you put a control down, do you have to declare a callback that the control?
Not necessarily. Yeah, so you can have a callback where if you have a change in the control, it'll generate a callback. In fact, with that G4P, that was, by default, they generated a little callback example for you that you could then modify. But the other thing you can do is you can just query the object. That's typically what I do in most cases, unless it's a button, for example. But if it's like a slider, often in my draw loop, in fact, here I can illustrate, let's see.
Does it add the callback for you, or do you have to add it if you want?
It adds it for you in the case of G4P.
Yeah.
And that's handy because a lot of times those are a pain. You have to go look for look for what you need to write, that sort of thing. So yeah, it adds it. Let's see.
Do you think the frame rate or the loop rate, it might be, does all its processing, but kind of what is the gating factor is when you get the next frame in, right? So it may be waiting on that, and that's what may determine the loop rate. Is
Possibly.
how,
Possibly.
your frames are.
One of the demos that he showed, the very first line was if something is available, it wasn't serial, it was image or something.
Right.
Yeah. So, yeah, it could just be the rate of the camera
Yeah.
capture device.
Now, in this case, I am, in fact, in this robot arm, I'll just fire it up just briefly, again, so Paul can see it, or anybody that wasn't here. And then this one is throttled by the availability of a frame. And I might even have a 15 frame per second. Oh yeah, so Paul, this is the robot arm, and what we did is we've got a, let's see, we're showing little registration points to help us locate where the arm is, and we can show where it thinks the center of the hand is, whoops, when it's not confused about that. I have, there we go, it seems to be doing, and I can manually control the arm. Okay, so well, here's an example. These controls, for the most part, I am just sampling their values. For example, this elbow control is generating, I can ask for its value, and I do that at the appropriate time rather than have it generate a event.
So you don't have to
Yeah.
generate a callback, you can query the
I
control.
can query the
Comes
control,
back.
yes.
Okay.
And the same with
Thanks.
like this threshold slider for, in this case, red. I'm using mostly for my blob detection. This one is being queried every frame. And then, of course, some things, like, yeah, whether we show different things here, those are also, oh, thank you. Oh, and to show you, Paul, here we have this hand map. Oops, say we will. Maybe we won't. Okay. Okay, I'm not good. For some reason, I'm not seeing the, oh, I need to load
The
the
demo for me, I was like.
No, that's okay. You were late. That's okay. You'll see it. But here's the map of all the locations as we swept the arm out. And that was used as a dummy approach to finding what elbow orientations equal what XY position on the screen for the purpose of grabbing the puck. But in my case, we can, oops. Here I'm faking a puck position with a mouse click. There we go. Okay, let me show you just a little bit about this, and I'll conclude here in about 3 minutes. Okay, so this processing program evolved pretty quickly out of really an existing blob detector. Sorry, as I scroll through all this, warp speed. I have an existing blob detector that I wrote some ages ago. In fact, it probably goes back 10 years ago. And this code, I'm just going to kind of scroll through it a little bit, implements a thing that locates blobs by taking what is actually already processed as a binary image. That red image we saw in up the right-hand corner, pretty much what I reduced the original color image to, we'll call it black and white or black and red. And anything that was red, there's an algorithm that is run, and it's available on Wikipedia. I forget the name of it. It's a 4-point search thing that's pretty good at scanning an image and finding the extents of regions. And then those regions you can return, in my case, I query those regions to find out what their extents are. And by extents, I mean like how far up, left, right, and down. And then I use those to create a little box around the, in this case, like if it was a puck, a little blob of pixels, you get a nice box. In that box, I can ask it what's the center of the box, how wide, and how tall the box is. And that's what I'm using for this thing. Anyway, so what this amounts to is a Java class or an object that does that processing. And it, in turn, builds a list of these blobs, and I can ask it, okay, I want to scan the list of blobs. And it knows a few things. It can tell me what the distance from a given blob to another blob is. And that was real important for me asking. I wanted to know, two of the closest blobs were my hand. You know, I had a hand, a blob on the wrist and a hand on the fingertip. And when I found what looked like two blobs that were about 50 pixels apart, that's my hand. And then I could use that to calculate the center of the hand. So that's the blob part of this beast. And so I'm just looking at how many lines of code. Yeah, it's about 500 lines of code for the blob detector. Then I've got some other stuff, like to do the arm calibration, for example, to make the arm sweep through the pattern and cover the whole screen is like a looping situation where we step, you know, the elbow, and then we step the elbow will step from a minimum to a maximum and go back and forth, or we step the shoulder to make that sweeping pattern. So there again, we've got a little program that's designed for calibration. It's about 300 lines. And then the original main program starts out along with accessing a graphical user interface that does not have a builder like I showed you earlier. This one you just look for examples, but there are examples. And in my case, just to give you an example here, we've got things to define the sliders, and they have a set of methods to set the position, the range, you know, the height, the size, you know, everything. And same with buttons. And for shorthand, I think I actually created methods that help fill in most of the stuff, and I just give them a few things. Like, for example, define button has a whole bunch of stuff that's the same every time. And for some reason, I won't go into that video. Anyway, so a lot of that stuff is the same from button to button to button, but what changes is maybe the name and the location of the button. So I have a little thing to help cut down on how much code I have to write. So in other words, this method gets called down here. Let's see, for example, here, when I define my buttons, test arm, calibrate. There I just gave the name and the location. And one weird thing about this, that it's a little tricky, is it turns out that the name, the label you give there to the button, like test arm, generates a method. You then, to catch that button when you press it, you need to write a method called test arm. So that's, I don't know, that could be a little weird, because if I went in here and changed this to test arm, or test 2 arm, now I've got to remember to go back and change my code. So there are little things, but again, stress, look at the examples and start simple. You start with 10 lines, press a button and have it light up a circle on the screen, and then do that, and then you move on. So anyway, I guess that's my presentation. Any questions? Yes,
Yes.
Pete?
You're going to have Will talk a little bit about how to interpolate the
Yes.
positions.
Okay,
Yes.
Ron, could you cover, you're obviously talking to the arm, you're talking to the robot arm. So you're talking over serial port, right?
Yes. Oh, I failed to talk about that.
Yeah. Can you?
Let me show you just, so that interface to talk to an Arduino arm, I'll just hit that real fast. So here we have the sliders, and then ultimately under program control, the arm is moved. But let's look at just what the code looks like to do that. Okay, forgive my scrolling around here. So we have an object called serial, and it's supported by a library. And I think that might be a library you have to install separately. And that was done up in there in SketchAdd library. So I've got this object called serial here. And forgive me for not having a simpler example just right here and now to show you this. And then down here, we can get a list of the serial ports, and that's what happens here. And I'm cheating. I'm just taking the first serial port in the list that's returned and instantiating a serial communication at 115,200 baud over this, what really is a virtual serial port that talks to the Arduino, just like you normally would talk to a gizmo like this. So anyway, and then the code that actually sends the ARM low-level commands more or less looks like, with the exception of a little code to detect things that are out of range, I'm writing these bytes right here. So these 5 writes, I start with an FF, all ones in a byte, so a sync byte, and then I'm sending really just 2 positions. And what I do is, so that I don't generate an FF in the second byte or a 255, I send 7 bits in that byte. And then I send the higher, what's remaining of that in the next byte. So that's what this is. And so this is a little bit of, if you haven't seen Java or C, what is this stuff? This is where you learn about bit operations. But yeah, what this does is sends the lower 7 bits, then shifts my shoulder number over 7 bits and sends that part, which is about 3 bits worth. And then I do that for the elbow. And running on the Arduino then is a sketch of about 20 lines. In fact, on the Arduino end to receive this, I can just real quick show you what the Arduino sketch looks like.
So the single flag doesn't, do you ever get tripped up by that or
Well,
misinterpreted?
Well, I don't think so. In other words, I could do some checking, but when I'm in my packet receiver, and keep in mind, I'm sending lots of packets. So in my packet receiver, I wait for the FF.
Yeah.
And so I have to have an FF before I say that I'm going to start processing what follows.
Yeah.
So if I start up in the middle of stuff, I'll just ignore part of the packet.
Okay.
But then what will happen is I'll find that FF, and now I'll sequentially read the next 4 bytes, and then put together my elbow values, and then thanks to Arduino, I have the ability to write the data out as time in circle type pulses between 1 or 2 milliseconds. And so thus I do that. And in fact, I guess it's done in microsecond resolution. let's see, so down here, somewhere, oh, there we go. Yeah, write microseconds to one pin that's being pulse width modulated, and then write the other one out there so that every 20 milliseconds, or whatever it is, or 50 milliseconds, wait a minute, 20 milliseconds.
Right.
Every 20 milliseconds, a servo pulse is written that's somewhere between 1 and 2 milliseconds wide, based on my original number that was between 0 and 1,000, coming from the processing environment. So anyway, I intended to talk more, but I'm glad I didn't, about other schemes for sending more data. I've done a lot of telemetry type stuff between robots and PC stuff over the years. This is one of the simplest here.
I tell you what, Ron, that sounds like that would be a good talk for later in the year.
Oh, okay, yeah, maybe that'd be a good talk.
Yeah.
Yeah, we could have something.
I know
a little
I
narrower
I
scope.
for one could benefit from that.
As a matter of fact, on our club robot, we've got our display and the brain piece, the main Arduino runner.
Yeah.
And we still need to write that interface.
Oh.
You might be able to help.
Yeah, that would be a real good example. We'd all
Anyway.
learn a lot from that, Ron.
Well, I'm not saying, in this case, I think I learned this scheme from a serial mouse. I think serial mice use something like this, where they have a byte that will never occur in the data. And I've used a similar, maybe not quite as robust, where what I say is if I happen to have, in my case it was a hex 80, if that's in my data, I repeat it. And so in other words, an 80 is represented as 8080, but then otherwise I have some command sequences that, anyway, you make it a synchronizing type thing. But I think that's not as foolproof as this.
I think Steve and I will come back and talk to you about this. Okay, thank you.
Well-
FA is used as a flag also. I don't know why that was picked,
Hmm.
but, yeah, seems to work though.
And if 00 are pretty good partners.
Oh,
Yeah.
yeah. Okay, so Will was going to, should I display that diagram? Oh, no, what we should do is,
Let me talk a little bit,
okay.
on the calibration.
Well, do you want me to display kind of that sweeping pattern again?
No,
Okay, you don't need to see that, okay. And you could always talk to the whiteboard. But you want to see your,
just hold it.
okay, I'll shut up. Okay, you come up
I'll
here.
ask you to display mine.
Okay, you want to come around here and sit or stand or whatever you want to do?
Oh, I'll probably stand. Maybe I'll stand.
Okay, oh, yeah, here. Yep. And I'll sit you here.
Basically, the problem that we're trying to solve here to a certain extent is we won't be able to drive the hand to a given XY coordinate. Basically, what this original design was, we put the puck somewhere here and the arm was the home position. And you could put the puck anywhere, you could reach out and grab it and shove it off to the other place, go back and, but basically the problem is the camera finds the puck. Now the question is, how do you position the hand where you want it? The calculation of knowing where the hand is, if you know where the angles are, is relatively simple. The equation for the X position is it's a cosine times the arm length plus another trait function times the other arm length, and that's it. But the inverse problem with that is given the position of the hand, X, Y, how do you calculate the angles? And that turns out to not be as easy. It's not really very difficult, but at least so far I've not come up with a single equation for it. It's just kind of a procedure. It's really pretty simple. You've got to solve the right triangle, which is basically basically, you know, you got a line drawn from the center of the elbow, center of the
Shoulder, center of the shoulder.
Center of the shoulder and center of the hand. Okay, you can calculate that angle, the angle of that line, and you can calculate the length of that line pretty easy. All right, if you know the distance between these, then you've got a triangle that you know all three sides. And so if you know all three sides, you can calculate these angles, and basically you're almost there. If you do what we did here and make two arms the same length, the solving the problem for this three-sided triangle is not very difficult. So that's really not a difficult task. You know, just solving the right triangle and finding the angle, solving a little bit. But in order to use that, you have to calibrate it. And that basically says you've got to know the camera calibration, that is, how many pixels there is per inch here, and it may be different in X and Y. You've got to know the position, the pulse width, to position the arm at 45 degrees to the camera's X, Y. You've got to know the pulse width for the elbow to get it at 90 degrees. And then you have to know the change, the calibration, how many degrees per pulse width. So you wind up with a fair number of calibration factors that you need to know. And I came up with a way, a procedure, not code, but a procedure that if we put the dots on here so we could look and read those camera levels.
Yeah, did you, what was the first step? Did you put it in a vertical or? I can kind of, give me a show you the
It was
diagram.
vertical, it was round and vertical.
Oh,
But
okay.
basically what he meant to is, if you put your arm in three different positions, then you could go through a bunch of calculations and come up with calibration factors. Well, it took me too long to come up with that procedure, so in the meantime,
I couldn't handle it.
we discussed it would be desirable if you didn't have to have all that calibration data. And so that's when Ron came up with the idea of doing a grid calculation. So he came up with that procedure. But it still leaves the problem as it only gets us closer to the target. Because there's a finite number of calibration points. So the question then is how do you know how far you've got to change the two angles to move it to where you want it? And you got the same problem. It's relatively easy to know how far you've got to move. If you move the angle a little bit, you know how far the hand moves. It's relatively easy. But the opposite of that is not true. So the question is, how do you solve that problem? And in the in scratching.
Okay. You want to see the diagram?
No,
The formulas?
yeah, the formula.
And scratching. Oh, my.
I apologize for the quality of this side, but,
It gets the point across pretty well.
huh?
It gets the point across pretty well.
Well, it's not really all that difficult. Basically, the very top line up there shows you that you can calculate the change in X as a function, or let me say this. U is the one of the angles, B is the other angle, and of course X and Y are the coordinates of the hand out here. And PXU is kind of notation for your calculus people. That's part of the partial derivative of X with respect to U. And actually, it's not difficult to calculate that if you know the parameters. But it turns out the data that he took with his stand has that data. Because you know where one point is, so you can get that data. So it's pretty easy. You can get PXU and PXY and B, and those four numbers you can get off of this data. But what you really want is you want to have DU as a function of dx and dy. And so the question is, what are those partial derivatives? And the way I came up with it, if you take the top two equations and solve them for du and dx, du and dv, you have those values. And that's my calculation. Basically, I came out with the fact that when we see the values for the function. So that's the approach I hope to take is, we know how far we need to move, we can extract and calculate the four factors there, and hopefully then move.
So that's essentially your linear interpolation between your points.
Yeah, it's kind of a linear interpolation, but it's because
But it's not,
It's a two-dimensional problem.
but it's, the data isn't aligned, right? I mean,
if you plot the points, they're not, they're not on a rectangular grid.
Right.
They're on they're a different shape as you go.
Right.
It took me a little while to realize this was possible the way to do it. Have I, any questions or any arguments?
Well, Ron, can you flip the actual calibration data back up?
Oh, you mean the sweeps
Yeah.
as they were being made?
Yeah.
Yeah.
Okay, can you bring the, all right, so in a sense, this should be able to map, what you really, if you try to interpret this, let's see, how do I want to say this? All right, so each sweep represents from minimum to maximum on some given elbow angle, right? Otherwise, you have the elbow. Is this called the elbow?
So
Is
like
this-
where I have the mouse cursor right now, look,
Yeah.
you can actually see that circle thanks to a few being missing.
Yeah.
So right there, right, so at that position, that is an example of if we had a puck here with a center right there, it would be perfectly aligned and we have
Right.
no error whatsoever.
Is this the elbow? And what's
No.
what are the two
The
terms?
elbow and the hand and the shoulder is back here, yes. so the-
Okay. All right.
um,
So each sweep represents a set shoulder,
Yes, with a
a
sweeping
set
wrist.
shoulder, and a sweep of the elbow.
Sorry, yeah, sweeping elbow, yeah, now that I'm using it.
Okay. So what I was wondering is, if you had this information, can you like transform it into from a rectangular grid into a grid that represents those two coordinates, elbow and shoulder. There's a shoulder, yeah, shoulder and elbow.
Well, at least it's theoretically possible. I'm not sure how to go about it right now.
Mhm. Well, I mean, there's it obviously sweeps like. I'm going to say that it's some sort of circle. Otherwise, the path could be represented by a circle.
Yeah. So what you're saying is to take this calibration and map it to where, instead of it being in terms of angles giving you a position giving you an angle.
Yeah, Otherwise,
And
instead of
in
thinking of
effect,
XY, instead of thinking of
taking this
XY, you think of elbow and shoulder.
Well, yeah.
I mean elbow and, yeah, elbow and shoulder.
Yeah, so at the moment, I guess this is apparent, so at the moment, what happens is we search when we have a puck in a given position, like whatever, somewhere. So at that given position, we search this table and we find at the moment, we find just the closest puck that was ever nearest that point, right?
Correct.
Okay, so here, Will, okay, so here, there you go. So here's you drawing your,
What I'm trying to say is, let's say, these lines are of constant view, and
okay, so that's a constant
Constant,
shoulder
these
with
are
a
constant.
varying wrist.
constant V is basically what that's what he's gone. He makes this line, and then he does this line, but basically what it amounts to is you can create a grid. It's basically, well, these lines are constant U, and these are constant V. And the problem is, you got a point here, and so you want to find out how to get to that. How much U and how much V. And so basically, what it amounts to, you know.
I think we're saying the same thing.
Huh?
I think, yeah, I think we're
So
saying the same thing.
you know, in that, so in your drawing there, Will, just for
But
somebody who might be looking at
basically,
it.
what I'm saying is, this is a kind of a local area. What I understood you to say is to do that globally.
But, yeah, well, I'm saying since it's so, if you look at the sweeps, they're so predictable. You know what I'm saying? So there's probably a transform that you could use. But what we're both saying, I think, is you take an X and Y and you transfer it into an arm and a shoulder position.
Yeah.
And so if you look at, so you need the function, the transfer function to go from X, Y to shoulder, arm.
Yeah.
Right,
Elbow,
and that's the
elbow,
lookup
I'm
table.
sorry.
Right.
He's doing, yeah, this is a lookup table, the way the approach
Right.
was. But I'm saying is if
And so,
you,
the information you have, just for someone, I think most people see it, but the corner points there, right, Will? So these points here are known, right? Like dot, 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 dot. Those are known points, right?
yeah,
Those are known points.
Yeah, so it's really just a matter of,
You know this point in both the U's, U and V coordinate and the X and Y coordinate. So basically,
In other words, you're looking for an equation, not using that.
and you might just, so you just linearly interpolate that,
you could do that. yeah.
right? In other words,
problem is, how do you interpolate between here, at least, and the way I came up with is, you basically calculate the partial derivative based on this, and then calculate the other, the inverse
okay.
partial.
Could I ask you, Will, just one question? I'm just curious. So like this situation here, so these are known points.
Yes.
I mean, could I just approximate it as visualizing it as whatever these points are and just linearly interpolating? Which,
What do you mean by linear interpolation?
oh, okay, so now I'm in trouble because I don't know if this is really skewed a bit more.
Well,
Let's draw it a little more like this. I got a point. Okay, maybe I don't know. Oh, I see. Well,
We can take it offline, we don't want.
yeah, all right.
Yeah, let's not,
All
let's,
right, we can.
You got all kinds of memory, all kinds of speed, just use the lookup table.
So, yeah, one way was really, that would get us close enough for this was to double the number of shoulder, cut the shoulder increments down.
I really think
But-
you can have the numbers. We don't need as many elbows as you have, and maybe a few more
Shoulders, okay.
Yeah.
One thing I will
Higher
say,
resolution in the
Yeah.
one and coarser in the other.
Yeah, yeah.
I think it may be possible to do the job without doing the calibration sweep.
Really? How would you do that?
Yeah,
Well, basically what I'm saying is,
It's an inverse kinematic.
if this is where our arm is, and this is where our target is, then we can Basically, instead of trying to go to this point here, we just go to this point here, which is on the way to it. All right, we know then the X and the Y, the delta X and delta Y that we've created here. We also know the delta U and delta V that we did put into it to move it. Okay, now, so if we assume the thing is kind of linear, we know that if we can
You
calculate.
do it basically by interpolating it as you go.
Calculating the D derivatives in the first equation I had,
Yeah.
and come up with the second equation, and then, so you keep working it together. And I think you can drive it over to this point.
It's sort of like doing wall following. So you can either do it by having a map of it in the first place, or just reducing the distance as you go.
Well, we'll see. Let's see if we get a good solution, then it'll make more sense, right? If we can produce something that works,
Yeah.
and it'll be worthy of a few minutes. Right.
Well, thank you for putting up with me.
Thanks, Will. Thanks.
Very
you,
good.
Will.
Okay.
All right. So, any other questions? We beat this pretty much into the ground. Good. Okay, somebody was going to do a show and tell.
Yeah, so that'll what we're gonna do next, is some show and tell. I think,
Hey, thanks for bearing with me, too.
Yeah, no
Appreciate
Well,
it.
thank you, Ron.
thank you.
Thank you.
Really good.
Yeah.